You know that feeling, that split second of confusion, maybe frustration when you just want to open a door, but you push and you should have pulled.
Oh, yeah. Or wrestling with a shower knob that seems designed by, I don't know, an evil genius to give you either ice water or molten lava.
Or the existential dread of trying to set a simple timer on a microwave that looks like the control panel for a spaceship, seriously.
Exactly. It's kind of bewildering how often everyday objects seem to fight against us.
And yet sometimes you encounter something that just works. It feels intuitive, effortless, almost invisible, like it fits you perfectly. Why is there such a massive difference?
That's really what we're getting into today. We're taking a deep dive into the surprisingly deep psychology of how we interact with the things around us, from coffee makers to complex software. We're exploring what makes some things a joy to use and others just a constant source of frustration. And we're drawing on insights from a really foundational book in this space, The Design of Everyday Things.
Right. So our mission here is to unpack the core ideas from this source material, to kind of give you the framework to understand the fundamental principles that separate the delightful designs from the dreadful ones, and, crucially, how those principles connect directly to how our own minds work.
We want you to understand why design really matters, far beyond just how something looks.
Okay, let's dive in.
Let's do it.
So when most people think about design, they probably think aesthetics.
Yeah.
Style, color, shape, that kind of thing. But the source material makes it clear it's so much more fundamental.
Absolutely. I mean, aesthetics are part of it, certainly, but the core idea is really about enabling interaction. Good design, as the book emphasizes, is often invisible precisely because it works so well.
You don't even notice it.
You don't notice the design when you effortlessly achieve your goal. Bad design, on the other hand, well, it's impossible to ignore. It stands out, it practically screams its inadequacies through every frustrating interaction you have with it.
So it's really about function and usability, first and foremost. What are the most basic principles the book introduces to get that right?
Well, first up, you have discoverability. Basically, can you even figure out what actions are possible with this object? What can you actually do with it? Where do you push, pull, turn, swipe?
Okay, so knowing what actions are options, and then...
Then comes understanding. So once you know actions are possible, do you understand how the product is supposed to be used? What do the controls actually mean? What's the intended sequence of actions?
Got it. So discoverability, what can I do?
Yeah.
And understanding how does it work and how should I use it? How do designers actually, build that in?
This leads us to two really critical concepts. They often get used interchangeably, but the source clarifies the important distinction: affordances and signifiers.
Okay.
Affordances are rooted in psychology. They are the possible interactions between a person and an object, determined by the object's physical properties. So a flat surface affords resting things on it. A knob affords turning, pushing, pulling, maybe?
Right, the possibilities.
Exactly. The book notes that in the design world, the term affordance was sometimes, let's say, loosely used to mean what an object looks like it affords, which isn't quite the original meaning.
And that's where signifiers come in, to bridge that gap.
Precisely. Because affordances aren't always obvious, or sometimes you need to know where to apply the action. Signifiers are the signals. They're marks, labels, icons, so really anything that communicates where an action should take place, or maybe what the state of the object is.
Like a label.
Yeah, a push sign next to a flat plate on a door is a signifier telling you to use the pushing affordance of the plate. A little blinking light is a signifier communicating a state change. You really need both.
So an affordance is what's possible, and a signifier is the cue that tells you how and where to act on that possibility. That hotel sink example from the book perfectly shows this failure, doesn't it?
Oh, that frustrating sink. Yes. No visible stopper control, right? You wash your hands, you go to drain the sink, and there's no obvious lever or pull thingy. You eventually discover, probably by accident or just frustrated prodding, that you have to push down on the stopper itself. That action pushing the stopper was an affordance, but there was absolutely zero signifier telling you to do it.
And the result?
The consequence. You have to put your nice, clean hands back into the dirty water. It's just a total breakdown of signifiers and, frankly, a lack of thoughtful consideration for the activity itself.
Oh, yeah, a visceral example of bad design. Okay, another key piece mentioned is feedback, how the object communicates back to you.
Crucial. Absolutely crucial. Feedback confirms that an action has been registered or maybe that the system state has changed. Did your button press actually do anything? Did the command go through?
Right.
Poor feedback, like, those annoying beeps that don't tell you anything specific or lights that just flash meaninglessly that can actually be worse than no feedback at all because it's just noise. It adds confusion.
Like the constant temptation to push an elevator button multiple times, even though you
Oh,
know you
yeah.
already pushed it, or hitting the pedestrian crosswalk button repeatedly. You might get a beep, but you get no real information about when you can actually cross. Your action got a response, but the feedback is, well, insufficient.
Right. Feedback needs to be informative, it needs to be timely, and ideally unobtrusive. That cacophony you get when multiple devices make similar generic alert sounds, that's a common frustration stemming from poor feedback design.
Okay, so we perceive things, we look for signifiers, we act, we get feedback. How do we actually make sense of it all in our heads?
Ah, that's where conceptual models come in. These are the sort of simplified explanations we build in our heads about how something works. We piece them together from the affordances we perceive, the signifiers we see, the feedback we get, and maybe documentation or past experience.
And these mental models can be completely wrong, which leads to massive frustration.
Precisely. The book gives that great example of the frustrating refrigerator temperature control. People turn it all the way up when it's too warm, assuming higher numbers mean colder, like an air conditioner.
I've done that.
We all have. And the manual in that case actually reinforced the wrong model. Their mental model just didn't match the system's actual model, and the design itself didn't help them correct it.
So there's the designer's model, how the designer intended it to work, and then there's the system image.
Right. The physical device itself, the controls, displays, manuals, that's the only way the designer actually communicates with the user.
And finally, the user's model, which is what the user infers based purely on that system image.
Exactly. And the fundamental problem is that the designer often assumes the user's model will magically match their own. But communication is imperfect, and it relies solely on that often ambiguous system image.
The pressure's really on the design then.
Totally. The onus is on the design, on the system image, to clearly convey the correct conceptual model. If it fails, the user creates their own model, and it's likely to be incorrect, leading to errors and frustration.
And just to complicate things, the real world of design isn't just about perfect usability, is it? Designers are always balancing conflicting requirements.
Oh, always. The purchaser, maybe the person buying for an office, might prioritize low cost and sleek appearance. The end user, the person actually using it every day, wants functionality and ease of use. The service department wants it to be easy to maintain.
Right.
The source mentions a stove purchase where the buyer prioritized features and the look over how easy the controls were to figure out, essentially sacrificing usability for other values. Design is inherently a series of compromises, and unfortunately, usability doesn't always win out.
Okay, that gives us a good language for talking about design interaction. But these objects are being used by, well, messy, imperfect psychological humans. So let's shift to the really fascinating part. The psychology behind our actions and, crucially, our errors.
Yes, because to design for people, you absolutely have to understand people, our strengths, our weaknesses, our weird tendencies. The book talks about the gulf of execution and the gulf of evaluation.
Okay, the gulf of execution.
All right.
That's figuring out how to actually do something to achieve your goal.
Right, bridging that gap between your intention in your head and the physical actions required in the world. And the gulf of evaluation is figuring out what happened after you acted. Did you actually achieve your goal, and can you tell?
Like the stuck drawer example.
Perfect example. The gulf of execution is figuring out how to work the release mechanism, whatever it is. The gulf of evaluation is pulling, feeling resistance, and needing to figure out why it didn't open and what the current state of the drawer is.
And good design, using signifiers, constraints, mapping, feedback, that's what helps us bridge those gulfs, make them smaller.
Exactly. The book also gives us the 7 stages of action cycle goal: plan, specify, perform, perceive, interpret, compare, as a way to kind of analyze where breakdowns might be occurring in that cycle.
It's a framework for thinking.
It's a useful analytical tool, definitely. But as the book reminds us, most human thought isn't really that conscious and sequential. We operate on multiple levels simultaneously.
Because most of our brain operates subconsciously, right?
Correct. Yeah, the vast majority. The source describes 3 levels of processing. The visceral level is the fast, subconscious, immediate emotional response, that gut feeling, like instantly recoiling from a sudden loud noise or the fear you feel standing near a cliff edge.
That raw, sort of instinctual reaction.
Exactly. Then there's the behavioral level. This is learned skills and actions, largely subconscious, triggered by patterns and situations. Riding a bike, typing, driving familiar routes, these often operate at the behavioral level.
Things we do without really thinking consciously about each step.
Right. And finally, the reflective level, this is our conscious thought. Reasoning, decision-making, contemplating, appreciating. This is where we analyze, compare, engage with culture and meaning.
So enjoyment involves all three.
Often, yes. The book suggests that really enjoying a product often involves all three levels: the immediate positive feeling, that visceral appeal, the smooth, effective use, the behavioral fluency, and the ability to think about and appreciate it, the reflective part. Even, logical engineers have visceral responses, like the satisfying feel of a well-made tool.
So we're definitely not purely logical beings. And our subconscious mind loves patterns and stories, which apparently leads to causal attributions.
We're natural storytellers. We constantly try to explain why things happen, creating stories even when our understanding is limited or maybe even wrong. The thermostat example again. People believe cranking the heat or AC way past the desired temperature will make the room heat or cool faster.
Guilty again.
It feels like it should work. We attribute a cause and effect that just doesn't exist in most standard thermostat designs. We create a story about how it works.
And this storytelling tendency, especially when things go wrong, often leads us to blaming the wrong things. The book makes a really strong and I think vital point here about blaming the user.
This is such a key takeaway from the source material. The shocking example of the 3 Mile Island nuclear accident control room design is used. Operators were blamed for human error, right? But later analysis revealed the control panel was so poorly designed, with confusing displays, hidden indicators, just overwhelming alarms, that operators making errors under pressure was almost inevitable. The design itself caused the error. The moral is stark. The design was fundamentally at fault, not the people trying desperately to operate a flawed system under immense stress.
Wow. That completely flips the script from stupid users making mistakes to systems designed in ways that make people look stupid.
Precisely. And that can lead to users falsely blaming themselves, which is a state the book calls learned helplessness. If you have repeated negative experiences with poorly designed technology, or maybe even academic subjects like math where you struggled, you can start to conclude, I'm just bad at this. You internalize the failure caused by bad design or bad teaching, and you stop trying. It becomes a self-fulfilling prophecy. It's really a tragic consequence of bad design.
But the flip side is that design can also embrace positive psychology and the idea of learning from failure, right? Especially in the design process itself.
Oh, absolutely. Failure during the development process is incredibly valuable. The IDEO design firm's creed, fail often, fail fast, really captures this. Prototyping, testing, seeing where things break or confuse users early on provides crucial feedback that makes the final product so much better.
And this perspective leads to a really powerful credo from the book. Eliminate the term human error.
Yes. Just get rid of it. Replace it with concepts like communication failures or interaction breakdowns. Most things we call errors are actually the system's design failing to accommodate normal human behavior, our flexibility, our creativity, our occasional, lack of machine-like precision. The example of a calendar program that intelligently parses dates typed in various formats, next Tuesday, Aug 15, tomorrow, that's a great example of technology accommodating human imperfection rather than demanding rigid, error-prone input formats. Make the machine flexible.
Okay, let's break down these non-errors a bit more. The source categorizes them into two main types, slips and mistakes. What's the difference?
Okay, so a slip is when you intend to do one action, but you accidentally execute a different one. Your goal is correct, the plan is okay, but the execution, the path you took, went wrong somewhere. These are the most common everyday errors we make.
Like typing the wrong letter. And there are different kinds of slips.
Several. Action-based slips happen when the wrong physical action is performed. A classic type is description similarity slips. This is where the item you act on is similar to the one you intended, often because of vague descriptions or more often similar visual or physical cues, like confusing coins of similar size or accidentally hitting the save button when you meant to hit send because they look alike or they're right next to each other on the screen.
Ah, okay. So the design lesson there is make things that do different things look and feel significantly different.
Exactly. Another action-based slip is a capture error. This happens when you intend to do a less frequent action, but a highly frequent habitual action takes over because the initial steps are similar.
Like driving home automatically when you meant to stop somewhere else.
Perfect example. Or the book's example of intending to unbuckle your briefcase but accidentally unbuckling your wristwatch because the initial hand motion is similar and very practiced. The design lesson there is to try and make the starting steps of similar procedures distinct if possible.
What about just forgetting to do something?
Those are memory lapse slips. You simply forget part of the planned sequence or you forget to check the result afterwards. Forgetting your briefcase entirely when leaving the house, that's a memory lapse slip.
And mode errors. They sound inherently tied to complex devices.
They absolutely are. A mode error occurs when a control or display has different meanings depending on the system's current mode. Think of a universal remote control where the number pad controls TV channels in one mode, but maybe DVD chapters in another mode.
Right, very common.
As functions proliferate in devices, designers often resort to modes to manage complexity, but this inevitably increases the potential for confusion and mode errors. The source mentions an Airbus accident that involved pilots making a mode error, misunderstanding which automatic flight mode was actually active at a critical time.
Okay, so slips are errors in executing a basically correct plan. Mistakes then are different. The plan or the goal itself is actually wrong.
Exactly. And they are much harder to detect than slips, often only discovered long after the fact. Because the actions you took felt perfectly appropriate at the time, given your incorrect plan or goal.
Why are they harder to spot?
Because everything seems fine as you're doing it. The example of complex process control plans with thousands of gauges makes this clear. You can easily miss the one critical indicator showing that your overall strategy, your mental model of the situation, is leading towards a potential disaster. You're acting correctly based on your flawed understanding.
Detecting and correcting errors sounds like it relies heavily on good feedback again, especially for slips.
Feedback is essential for detecting action slips, definitely. You feel the wrong button, you see the wrong menu item highlighted. But memory lapse slips are really tricky because, as the book points out, there's no action to see or feel feedback from. You just didn't do it. How do you get feedback for inaction?
Good point. And when mistakes do eventually lead to problems, our natural storytelling and that hindsight bias kick in, making it seem like the mistake should have been obvious all along.
Yes. The tendency to explain away mistakes with hindsight bias is a huge barrier to learning. It prevents us from truly understanding the contributing factors, the poor design, the situational pressures, the misleading information that led to the mistake in the first place. Everything looks crystal clear after the accident.
So if we were to summarize the key design lessons from studying errors, what would they be?
First, understand why errors happen, the psychology, the types of slips and mistakes, and then design to minimize those specific causes. Second, incorporate checks or confirmations, sensibility checks, but make them smart, not just annoying interruptions.
Like, are you sure you want to delete this? But better.
Ideally, yes. Third, make actions reversible whenever possible. The undo function is probably one of the most important usability features ever invented. For irreversible actions, make them require extra effort or confirmation. Fourth, make errors discoverable when they do happen and make them easy to correct.
And finally,
And crucially, reframe how you think about errors. Treat user actions not as failures, but as approximations towards a goal. The user is trying to do something, design the system to help them achieve the correct outcome, even if their initial action isn't perfect.
and we should quickly mention interruptions. They're a huge, often overlooked source of error, right? Especially memory lapse slips. And systems are often terrible at helping you resume where you left off.
Absolutely. Interruptions are killer for working memory. And when major failures do occur, the book highlights Reason's Swiss cheese model of accidents.
Ah, the Swiss cheese.
Right. It suggests accidents rarely have a single cause. They happen when multiple layers of defense or multiple system components have flaws like holes and slices of Swiss cheese that momentarily align, allowing a hazard to pass through all the layers. It emphasizes that safety requires layered design and systemic thinking, not just blaming the final person involved.
This still leaves that sort of uncomfortable question. When are people really at fault? I mean, the book acknowledges deliberate violations do happen.
It does. Sometimes people knowingly break rules or ignore procedures, The source mentions examples in aviation or scuba diving, but it argues often these are routine violations.
What does that mean?
It means the rules themselves are sometimes poorly designed, maybe outdated, or they make the job impossible to do effectively or safely if followed strictly to the letter. So people develop their own workaround violations just to get the job done.
So the violation is a symptom.
Often, yes, a symptom of a deeper design or organizational problem. The Air Florida crash is cited as an example where social pressures, schedule pressures, and institutional factors contributed to the crew making decisions that ultimately led to disaster. It's rarely a simple case of individual bad intent. There are almost always systemic factors pushing people towards risky choices.
So even when people deviate, it's often a sign that the design needs to better accommodate the realities of how people actually work and the pressures they face.
Precisely. And part of that accommodation is designing for recovery. When, inevitably, errors or failures happen, the design should make it as easy and safe as possible for the user to recover control or mitigate the consequences.
And this seems critical with automation.
Very. Compare the potential time a pilot has to recover from an automation failure in a modern jet, maybe seconds, sometimes minutes, versus the tiny fraction of a second a human might have to react if automation fails unexpectedly in a self-driving car at highway speeds. Recovery time and the support for it are critical design factors.
Okay, so the big takeaways for designing for people seem to be, don't assume people keep everything crucial just in their head. Use constraints, signifiers, mapping to put knowledge out in the world. Make things visible. Design anticipating errors will happen. Design for easy recovery. And standardize where it makes sense to reduce cognitive load.
That's a really solid foundation for creating less frustrating, more humane interactions with the things around us.
Speaking of knowledge not just being in our heads, let's talk more about that. The book makes a really powerful point that precise behavior can emerge from imprecise knowledge. How does that actually work?
It works because knowledge isn't confined just to our internal memory. It's also out there in the world. It's embedded in the physical environment, in the constraints of objects, in cultural norms, in external aids like lists or calendars. We cleverly combine the little bits we remember internally with the rich information provided by the world to guide our actions very effectively.
Like the coin examples. You mentioned Americans don't need to remember the exact diameter of each coin. We rely heavily on the size difference because our bills are all the same size. But someone from a culture with multicolored, size-varying bills might get confused by our similar-sized quarters, nickels, and dimes if they rely on color.
Exactly. Our environment, the structure of the information in the world, shapes what specific knowledge we need to keep in our heads and how we access the rest externally. The structure of the world provides crucial clues that reduce the memory burden.
The book distinguishes between knowledge of factual, arbitrary information and knowledge which is more procedural subconscious skills.
Right. And we are absolute masters at using the world for memory in the world. Writing notes, leaving objects in prominent places to remind us of things, organizing our workspace. These are all external memory aids. They reduce the burden on our very limited internal recall.
The coin example shows this again, doesn't it?
It does. The physical variation in size and maybe even feel of, say, French coins puts more knowledge in the world than the close size similarity of many U.S. coins. This changes how users rely on external cues versus internal memory for identification.
This ties directly into constraints being so incredibly powerful. They limit the possible actions based on physical properties or cultural norms or meaning or logic. They provide knowledge in the world by drastically reducing the set of choices you even need to consider.
The Lego motorcycle example from the book is perfect for illustrating this. You have physical constraints, pieces only fit certain ways. You have cultural constraints, putting the police stickers right side up, not upside down. You have semantic constraints, the headlight clearly goes on the front because that's what headlights mean. And logical constraints, if there's only one piece left and one spot open, logic tells you where it goes.
So all these constraints guide you through assembly without really needing detailed instructions or memorization. They're powerful forms of knowledge in the world.
Exactly, which is absolutely critical because human memory, particularly our short-term or working memory, is surprisingly limited.
Yeah, short-term or working memory, STM. The book says it has a very small capacity, like 4 items or something.
Something like that, yes. Maybe around 4 chunks of information you can hold and actively manipulate at once. Arbitrary things like long, random passwords overload it almost instantly. And critically, as we mentioned, interruptions can completely wipe its contents.
That electronic medical records example was chilling.
It really was. Nurses being automatically logged out after a short time, losing their context, losing the patient info they were just working with in their STM, and being forced to write things down on scraps of paper because the system doesn't support the reality of interruptions in their workflow. It's a perfect illustration of how poor system design completely ignores fundamental STM limitations.
And long-term memory, LTM. That's for the
Yeah.
past, but it's not like a video recording, is it?
No, not at all. It takes time and effort to encode information into LTM, and retrieval isn't perfect either. It's more of a reconstruction based on fragments and associations, rather than a perfect playback.
So the key difference for design seems to be remembering arbitrary things, is really hard names, random numbers, inconsistent procedures. But remembering meaningful things is much easier.
Much easier, yes. Because we can connect meaningful things to our existing knowledge structures, we can use rules, analogies, and constraints to help us remember or figure them out.
And this is where natural mapping really shines, right? It
Mm.
exploits meaningful relationships and spatial analogies between controls and what they control.
Exactly. Moving a control up moves the corresponding item up. Turning a knob clockwise increases the value. These feel natural because they relate to our physical experience of the world. Professor Sayeki figuring out those arbitrary light switches by drawing a spatial diagram of the room and mapping the switches to it. That's a beautiful example of someone imposing a natural mapping where the design failed to provide one.
And that diagram becomes their external conceptual model.
Precisely. Gesture-controlled faucets often use natural mapping, and stove controls that are spatially arranged just like the burners they control. That's ideal natural mapping.
They're so rare.
It is. As the book notes, most stoves still have that baffling linear row of identical knobs controlling a rectangular layout of burners. It's a terrible, non-natural mapping that forces you to memorize or constantly check, causing errors.
It's such a persistent, basic design flaw.
Mm?
And even culture influences how we perceive mapping, doesn't it?
It can, yes. Different cultures might have different conceptual models for things like the flow of time left to right versus right to left, which can affect the design of calendars or timelines.
Mm-hmm.
Even the now standard computer cursor movement, moving the mouse down, scrolls the window down, so the text appears to move up. That's a mapping convention that won out after some initial debate. It wasn't inherently obvious which way was natural.
So we navigate the world using this constant interplay between knowledge in the world and knowledge in the head. There's a trade-off, though.
There is. Relying too much on knowledge in the world can make us dependent or vulnerable if that information is missing, wrong, or changes. Think about blindly trusting GPS. But relying only on internal memory is simply impossible given its inherent limitations. Effective interaction uses both intelligently.
The example of pilots remembering air traffic control instructions is a great illustration of experts skillfully combining both, isn't it?
It's perfect. Pilots have deep knowledge how expert procedural memory. They make instructions meaningful by relating them to the flight context, knowledge in the head. But they also rely heavily on knowledge in the world. They write instructions down on a notepad, they enter clearances into the flight management computer, they use a sophisticated system combining internal and external memory.
That sounds like transactive memory.
Exactly. Transactive memory is how groups, or increasingly humans and technology together, distribute the tasks of encoding, storing, and retrieving knowledge. A couple might implicitly divide responsibility for remembering social engagements versus birthdays.
And human-computer teams.
A human-computer team is arguably the ultimate transactive memory system. We offload the burden of arbitrary recall and complex calculation to the machine, freeing our internal cognitive resources, our limited attention and working memory for higher-level tasks like goal setting, strategy, interpretation, and creativity.
That really reframes our relationship with technology. It's not just a tool we use. It can become an extension of our cognitive system. Okay, let's dive a bit deeper now into those constraints and conventions. They seem absolutely foundational to putting knowledge out there in the world.
They truly are. They are incredibly powerful forces that guide our behavior, often subconsciously, by limiting the sheer number of possibilities we need to consider. The source details the 4 kinds of constraints.
Okay, first up, physical constraints. These seem the most obvious, like a large plug won't fit into a small socket.
Right.
The laws of physics. Lego pieces only fit together in certain orientations. Good design can leverage these. The source mentions the Microsoft Instaload battery design, which uses clever physical shaping and contact placement to ensure a battery works correctly regardless of which way you insert it. It uses physical constraints to prevent error.
Clever. What's next?
Cultural constraints. These rely on shared social norms, conventions, and learned behaviors within a culture. How we greet someone, handshake, bow, kiss, traffic rules like which side of the road to drive on. The meaning of common icons or symbols, these often rely on cultural understanding. They constrain behavior through shared expectations.
Then semantic constraints. That sounds like it's about meaning.
It is. Semantic constraints use the meaning of the situation itself to guide action or interpretation. We inherently know the front of a car faces forward because of its meaning and purpose. We know not to put the police stickers on the Lego motorcycle upside down because that would violate the semantic meaning of a police vehicle. The meaning suggests the correct orientation.
And finally, logical constraints. These rely on reasoning and deduction. If you're assembling something and you have 3 unique pieces left and 3 unique empty slots and you figure out where 2 of them go, logical constraint tells you exactly where the last piece must go. There's only one possibility left.
So these 4 types of constraints, physical, cultural, semantic, logical, they act as powerful clues embedded in the world, limiting the set of possible actions and reducing the mental effort needed to figure things out.
Exactly. They make things easier. And cultural norms, conventions, and standards are particularly crucial for smooth interaction in society, but also surprisingly fragile sometimes. Traffic rules are mostly agreed upon conventions that allow complex systems to function.
Doors.
But the sheer variety in how doors open globally, push plates, pull handles, bars, knobs, slides, revolving doors, sensor-activated doors, it shows a spectacular failure of standardization, where a simple convention could significantly improve usability and reduce those everyday moments of frustration.
Yeah, the door problem. And within a single system, like a control panel, visibility and proper mapping are vital, as we discussed.
Yes, the examples of airplane switch errors highlight how poor mapping physically grouping controls far from what they control, or using similar-looking switches for critical but different functions can be incredibly dangerous, combining both mapping problems and potential description similarity slips.
Even basic residential light switches often fail this test. Designing intuitive controls for complex multi-light rooms is surprisingly hard.
It is. The source describes the author's personal solution using a physical diagram that maps the switches spatially to the lights in the room, a clever workaround that imposes natural mapping. But he laments the lack of good commercial solutions for this common problem.
It's amazing that such a frequent interaction remains so poorly designed in many homes and buildings. Now, sometimes constraints are used very strictly, deliberately, to force a specific behavior, right?
Yes, those are forcing functions. They are design elements that make it impossible to complete a desired action if a necessary preceding step hasn't been done correctly, or if the action itself would be dangerous.
Like needing the car key.
Requiring a key or electronic permission to start a car is a forcing function. Requiring a safety guard to be fully closed before a dangerous machine will operate is another. They physically prevent errors or unsafe operation.
And there are related concepts like interlocks, lock-ins, and lockouts.
Right. Interlocks prevent simultaneous, potentially dangerous actions, like engaging 2 conflicting gears. Lock-ins keep something engaged until a specific action is taken, like needing to press a button to release a plug. Lockouts prevent access or action entirely, like a safety lockout tag on machinery or child-resistant caps.
The dead man switch on trains or power tools, which stops the machine if the operator releases pressure, is a type of forcing function or interlock. Child-resistant packaging is deliberately designed as a lockout for small children, making it difficult on purpose.
Exactly. Forcing functions and related mechanisms are powerful tools for preventing critical errors or ensuring safety. But changing deeply ingrained conventions, even with seemingly logical new systems, can cause major confusion and resistance. The anecdote about destination control elevators is a perfect example.
Where you select your floor before you even get in the elevator.
Right. It completely upends the traditional model of getting in and pressing the button. Even though it might be more efficient, it violated a deeply ingrained convention and left users baffled, asking, why? This isn't how elevators work.
That really highlights how strong simple conventions can be, and the friction caused when they're changed unexpectedly.
Yeah.
Okay, reverting back to basic mapping problems, the single control faucet is still a source of daily frustration for many.
Oh, yes. That common pursuit of minimalist elegance often leads to terrible mapping. You have one control trying to manage both water flow and temperature. Which way do you turn or tilt for more flow? Which way is hotter or colder? Which direction do you push or pull for on-off? There are actually 4 distinct mapping challenges bundled into that one control, and different designs solve them inconsistently, forcing you to guess or scald yourself experimenting every time you use a new one. Usability sacrificed for looks.
Ugh. The source also discusses sound as feedback and signifier. We mentioned annoying sounds are bad design, but well-designed sounds can actually provide useful non-visual information, can't they?
They absolutely can. Think about the satisfying click of a key turning in a lock, or the distinct sound of different types of computer alerts. And sometimes sound is becoming necessary for safety specifically because of other design changes.
Like with electric cars.
Exactly. The increasing quietness of electric and hybrid vehicles, while nice in some ways, has become a significant safety hazard for pedestrians, particularly the visually impaired, who rely heavily on the sound of approaching traffic. The new U.S. standard requiring EVs to emit artificial sounds at low speeds is a direct design response to mitigate this unintended negative consequence. Sound is a crucial signifier and feedback mechanism.
That's a fascinating intersection of design, technology, accessibility, and safety. Another interesting concept mentioned is skeuomorphism. What's that about?
Skeuomorphism is when new designs imitate older technologies or materials, often unnecessarily. Think of early cars that were designed to look like horse-drawn carriages without the horse, or early computer interfaces with icons that look like physical folders, trash cans, or floppy disks.
To make them familiar.
Exactly. It can provide a sense of initial familiarity and comfort by referencing known objects, but it can also lead to arbitrary design elements that serve no real functional purpose in the new technology and might even constrain the design unnecessarily later on.
We've mentioned standardization several times because it seems so fundamental to usability in the real world.
It is. Standardization reduces the need to learn new things constantly. It ensures compatibility. It simplifies choices. The contentious choice of the HD TV aspect ratio, 16.9, based on a mathematical compromise, over adopting existing movie formats, is a classic example of how standards get set and have lasting, sometimes debated, impacts.
And once a standard is set,
It's incredibly hard to change. Establishing or changing standards is brutally difficult due to inertia, cost, and existing infrastructure. The ongoing metric versus English system battle in the US is the prime example. The failure of seemingly logical decimal time systems, like swatch beats back in the day, shows how conventions tied to natural cycles like day and night are almost impossible to overturn, even if they seem mathematically pure.
and the QWERTY keyboard, still with us.
The ultimate example. A standard locked in by mechanical constraints preventing typewriter key jams, and aggressive marketing in the late 19th century, now completely dominant despite slightly better, more efficient alternatives like the Dvorak layout existing for decades.
Why didn't Dvorak win?
The cost of retraining millions of typists, the cost of replacing keyboards, the fact that Dvorak's advantage wasn't huge for casual typists, and honestly, QWERTY isn't terrible once you learn it. It all meant the established standard persisted. Cord keyboards, which were even faster for experts, failed for casual users because they required too much complex knowledge in the head. QWERTY puts more knowledge in the world via the labeled keys.
So standardization provides valuable structure and reduces the need for arbitrary memorization, but it can also ossify designs based on outdated constraints or historical accidents.
That's the trade-off. And just to round out this section on constraints and conventions, the source does acknowledge that sometimes things are deliberately made difficult. Not all design aims for effortless ease. Right. Security systems are designed to be difficult for unauthorized users, obviously. Child-resistant packaging is deliberately designed to be hard for small children to open. And many games are specifically designed with challenges where figuring out the interaction, solving the puzzle of how to use the controls or navigate the world, is a core part of the fun. Think of adventure games where you have to figure out the magic words like "open Sim Sim" to open the cave in Alibaba.
So difficulty isn't always bad design. Sometimes it's the point.
Exactly. Not everything is, or even should be, effortlessly easy for everyone all the time. Context matters.
A crucial nuance. Okay, we've covered the core principles, the psychology, the knowledge in our heads versus in the world, and the power of constraints and conventions. Let's try to root all this into the messy reality of design in the real world. Business, innovation, and the future.
Right, because design doesn't happen in a vacuum, does it? It happens inside complex organizations, often involving multidisciplinary teams, engineers, designers, marketers, sales, manufacturing, who frequently have conflicting requirements.
Like we mentioned earlier.
Yes, like with the stove or the famously complex office copiers. The internal focus on sales price or hitting a feature checklist or manufacturing cost often overrides usability concerns, leading to products that look good on paper or in the showroom, but are frustrating to actually use day to day.
How do designers navigate this? The source introduces the double diamond model of design, as a way to visualize a structured process.
It's a useful model. It basically describes two main phases, and each phase involves both divergence exploring widely and convergence focusing down. First, you diverge to really explore and understand the problem space. Then you converge to clearly define the right problem you're trying to solve.
Okay, find the right problem first.
Then you diverge again to brainstorm and develop lots of potential solutions to that specific problem. And finally, you converge to refine, test, and deliver the final chosen design solution. Find the right problem, then find the right solution.
And fitting within that overall model is the human-centered design process.
Yes, this is the iterative engine, really, often called the spiral method because you keep cycling through it. It typically starts with observation, going out and understanding your target users in their actual environment, seeing their real needs and behaviors. Then ideation, brainstorming potential solutions based on those observations. Then prototyping, quickly building rough, testable versions of those ideas. And finally, testing, putting those prototypes in front of real users and getting feedback.
And then you repeat.
And then you repeat the cycle, using the feedback from testing to refine your understanding, generate better ideas, build better prototypes, and test again. This iterative process, this constant learning and refinement is absolutely key to arriving at a good design.
This seems heavily reliant on good design research then. What methods does the book mention?
Several. Borrowing methods from anthropology and ethnography is key, observing users in context, in their homes or workplaces, to see what they actually do, not just what they say they do. There are also quantitative methods like surveys, A/B testing, analyzing big data usage patterns, and of course classic usability testing.
Watching people use prototypes.
Exactly. Watching users attempt to perform tasks with a prototype or an existing product. The tip about sitting behind the user during testing or watching video recordings later is crucial. You want to see their hesitations, their errors, their nonverbal cues of confusion or frustration, not just rely on their self-reported opinions afterwards.
And the goal is different from marketing research.
Yes, a key distinction. Design research aims to uncover deep, often unarticulated human needs. Marketing research often focuses more on gauging existing wants or reactions to specific features. Good design tries to solve the underlying need.
And getting the requirements right through this repeated study and testing is essential, especially because, as the book notes, those seemingly special cases or edge cases often turn out to be the majority of real-world usage. Systems need that flexibility.
Absolutely. The diversity of users and situations is immense, which is why activity-centered design is often presented as a valuable approach. Instead of trying to design for some mythical average user persona,
Which doesn't really exist,
right, an average of a left-hander and a right-hander is useless for designing scissors. So instead of focusing on personas, activity-centered design focuses on supporting the activities people are trying to accomplish.
And the book briefly distinguishes between tasks, the specific steps, and activities, the higher-level goals or sets of tasks.
Yes. Activity-centered design focuses on supporting that higher-level activity. For example, instead of just designing controls for accelerating and braking tasks, you design for the overall activity of driving safely and efficiently, which might lead to broader solutions like better visibility systems, collision warnings, or integrated navigation things that support the whole activity.
Moving into design and practice, though, we see the real-world challenges pile up.
Oh, yeah. Multidisciplinary teams often struggle with communication engineers, marketers, designers. They all speak slightly different technical languages and have different priorities, and the ever-present budget and schedule pressures constantly threaten to cut corners, especially on that crucial upfront research and iterative testing.
The anecdote about the product manager always saying, "We'll do the user research next time," which somehow never comes,
Yeah.
that feels painfully real.
It rings very true for many people working in product development. It really highlights that creating good products isn't just about having smart designers. It requires a harmonious, cooperative organizational culture that genuinely values understanding and meeting human needs and is willing to invest the time and resources to do it properly.
And the fundamental challenge of designing for everyone remains immense. You simply can't design for an average person.
You can't. You need to understand the range of human abilities, disabilities, contexts, and goals, and design for flexibility and adaptability or offer different versions or modes.
Standardization comes up again here as a huge real-world factor influencing design choices and possibilities. We talked about HDTV aspect ratios, the metric system.
And QWERTY, the classic example of a standard locking in a potentially suboptimal design due to legacy constraints and the enormous costs and inertia involved in changing something so widely adopted.
Standards are powerful, essential for compatibility and reducing learning curves. But they are artifacts of their time and context, and incredibly difficult to dislodge once established, even if better alternatives emerge.
That's the double-edged sword of standardization.
The book also looks at the nature of innovation itself. It distinguishes between two main forms.
Yes. Incremental innovation, which is the gradual improvement of existing products and services. This is by far the most common type of innovation we see. And radical innovation, which involves fundamental shifts, often enabled by brand new technologies or a complete rethinking of the meaning or purpose of something.
Everyone chases radical innovation, but it's risky.
Very risky and rare. And the adoption of genuinely new technologies often takes a surprisingly long time. We're talking decades, sometimes even centuries, from the initial invention to widespread everyday use.
Why so long?
Several reasons. Large established companies are often conservative and risk-averse. Radical ideas often fail initially. Sometimes the ideas are simply too early. The supporting technology, infrastructure, or market readiness isn't there yet. The Apple QuickTake digital camera in the 90s was a precursor to smartphone cameras, but largely failed because the ecosystem for sharing and viewing digital photos barely existed then.
Or the video phone prediction.
Exactly. The prediction of video phones back in 1879 took over 100 years to become commonplace, with technologies like Skype, FaceTime, and Zoom requiring advances in computing, networking, and cameras. Radical change takes time.
And in the meantime, existing products often suffer from featureitis, that relentless pressure to just add more and more features.
Oh, yes. It's driven by customer requests. Can it just do this one more thing? By competition, our competitor just added feature X, so we need it too. And by market saturation, how do we differentiate the new model? Add more features.
Cars, refrigerators, phones.
They all tend to bloat with features over time, often becoming more complex and harder to use as a result. There's constant pressure to add new features, but rarely dedicated budget or time to go back and improve the usability or integration of the existing ones. The complexity just accumulates.
It makes you wonder, as technology keeps accelerating at this incredible pace, will people stay the same?
Oh.
Will our fundamental psychology change?
That's the million-dollar question, isn't it? Our core psychology, those 3 levels of processing, our basic memory limitations, our tendency to make causal attributions and tell stories that seems remarkably constant across millennia. Our brains haven't fundamentally changed structure in a very long time. But emerging technologies like truly seamless augmented reality or direct brain-computer interfaces or sophisticated AI companions, these could potentially start to change our perception, our interaction with the world, maybe even our sense of self in ways we can't fully predict right now. It's possible the tools could start to reshape the user in more fundamental ways down the line.
But for now, and for the foreseeable future, technology primarily functions as things that make us smart.
Exactly. It enhances our cognitive capabilities. It offloads tedious tasks like calculation and rote memory recall. It reminds us of appointments. It helps us navigate complex environments. The argument you sometimes hear that technology is making us stupid because we maybe remember fewer arbitrary... It really misses the bigger picture. We're not using our limited brain capacity on that anymore. We're using it for other things.
Like the chess player example from the book.
Perfect illustration. The best chess player in the world today isn't a human, and it isn't a computer. It's consistently a human-computer team where the human guides the strategy and evaluates complex positions, and the computer handles the deep calculation and remembers millions of opening moves.
So, combined, we're smarter.
Yes. Humans, augmented by technology functioning as a vast external memory system, as a transactive memory partner, are capable of far more complex thought and achievement than either could manage alone. Technology frees our internal cognitive resources for higher-level thinking, creativity, planning, and making meaning out of information.
The book also touches briefly on things like the future in books, maybe becoming more multimedia, and the importance of experts for quality content, and also the moral obligations of design.
Right. Moving beyond just usability and aesthetics to consider the broader impact. Thinking about the environmental impact of products throughout their entire life cycle, from manufacturing to disposal, designing for sustainability, even considering the social and ethical implications of business models like subscription models for digital content versus ownership. Design has a responsibility that extends beyond the immediate user interaction and the company's bottom line.
So pulling all these diverse threads together, it seems successful design isn't just about building functional objects or, making them look pretty.
Not at all. It requires a really deep understanding of human psychology, how we perceive, how we think, and how often we don't think consciously, how we remember and inevitably forget, why we make errors, and how we learn and adapt.
And it's not just psychology.
No, it also requires navigating that complex, messy landscape of business realities, conflicting internal requirements, budget constraints, schedule pressures, and the ever-changing technological environment. It's a synthesis of many disciplines.
Technologies will obviously continue to evolve at a rapid pace, but the fundamental principles of human-centered interaction, making things discoverable, understandable, designing for our cognitive strengths and weaknesses, gracefully accommodating error, those principles seem remarkably permanent, don't they?
I think they are, because they're rooted in the relatively stable nature of human cognition and perception. Good design respects that constant foundation, even as the surface technology changes.
It's really about creating interactions that feel natural, maybe even invisible,
Yeah.
and reduce the friction and frustration in our daily lives.
That's the goal, making the complex simple, or at least manageable.
So as you go about your day after listening to this deep dive, maybe look around with fresh eyes. Pay attention to the everyday objects you interact with. Which ones feel intuitive, almost invisible, like they just fit you perfectly?
And which ones make you pause, feel clumsy, maybe even a little stupid or frustrated?
What does that tell you, not necessarily about yourself, but about their design?
Try to notice the signifiers or lack thereof, the feedback or lack thereof, those moments of confusion, and maybe those occasional moments of simple delight when something just works beautifully.
The design of everyday things is literally everywhere, shaping our experience of the world in countless ways we rarely stop to consciously consider.
And now, hopefully, you have a slightly clearer lens, a better framework through which to see it and understand it.
Thanks for taking this deep dive with us.